Okay, so we're going to build off of our idea of limits, and we're going to look at an application of limits which allows us to find instantaneous rate of change. Okay, so if we're going to drive 200 miles, and let's say it takes us 4 hours, I want you to think about how fast were you going on average? What was your average rate of change? Your average speed would be the 200 miles divided by 4 hours. On average, you're going 50 miles per hour. So the change in distance over the change in time. Now, important to understand that this doesn't mean that you were going 50 miles an hour the entire time. At some point in your trip, you might have been going a little bit faster. Maybe you're going 65 miles per hour. At some point, maybe you're going slower. You're going 40 miles per hour. That would be your instantaneous speed, how fast you're going at one point in time. That'd be the speed that shows up on a radar gun. So we have a rock falling from a high cliff, and the position is given by y equals 16t squared. So t represents time in seconds, and y is the height in feet. At 0 seconds, we can plug that in. We find that we're at a height 0. At 2 seconds, 64. So this rock has gone down 64 feet. The average speed would be the change in distance, how far it's gone, over the change in time. On average, the rock was going 32 feet per second. So you know at the start, the rock was going slower than 32 feet per second. When it finished at 2 seconds, it was going faster, and it was changing all throughout that time. But on average, 32. So now it's the question we want to ask ourselves is, what is the instantaneous speed at 2 seconds? If you had a radar gun on that rock right there, how fast is it going at that moment in time? So instantaneous speed, we can take a very small change in distance over a very small change in time. So if we start at 2 seconds and we go to 2.1 or 2.01 or 2.00001, that's what we're showing right here. So h is some very, very small change in t, 0.00001 seconds. And we can take our initial or our final position, which would be given by 16t squared, in this case 16 times 2 plus h, that's 2.00001 squared, minus 16 times 2 squared, all divided by our change in time, which we're calling h. And we're going to investigate this with our calculators. So you can type in 16 times 2 plus h squared minus 64, so we just simplified the right side, over h. This vertical bar right here, such that is found by hitting Control equals. And the set brackets are down, hit Control, right parentheses, and you'll get those set brackets there. And this is telling the calculator to solve that equation for h equals 1, 0.1, 0.01, and so on. And if we look at the output there, we can see that we're getting very close to 64, meaning at 2 seconds, the rock is falling at an instantaneous rate of 64 feet per second. So it has a limiting value of 64, meaning as h approaches 0, the instantaneous rate of change is approaching 64. And we learned the other day that we can write this out using a limit. This is what the concept of a limit is. As our change in time approaches 0, we can find that instantaneous rate. So we can evaluate this algebraically, factor out a 16, 2 plus h squared, simplify, cancel out the 4s. Now we can cancel out an h from top and bottom. So we have 16 still, and now we can just evaluate by substitution, plug in h equals 0, and we get 64, which confirms what we thought it was by investigating with the calculator. So we found the instantaneous rate of change at time equals 2 seconds. So here's another one. We have the position given by this equation right here. S is commonly used for position, not speed. So make sure you understand when you see S of t, that's typically for position. The average rate of change from t equals 0 to t equals 5. So average rate of change, we need to know our our change in position over our change in time. So we find the position at 0 and the position at 5, we subtract those, we subtract our times, and we evaluate -1 centimeter per second. The average rate of change is -1 centimeters per second. Now we want the instantaneous rate of change at t equals 5. How fast are we going when time equals 5? So we use our limit. Limit as h goes to 0 of our position at 5 plus h minus our position at 5 over h, because again, h is a very small change in time. So we can plug that into our equation, expand and simplify, cross out all these common factors, cancel an h, substitute, -6 centimeters per second is the instantaneous rate of change. That's how fast it is moving at time 5. And notice that since the rate of change is negative, that implies that it's moving to the left if our motion is left and right. If the motion was up and down, that would imply that it's moving down.